Hi everyone, this is a quick demonstration of a typical projectile motion question. So I've set up an x-axis here and a y-axis. The origin of my coordinate system is at the starting point of the particle, which is a very typical choice to make. The projection speed for this is 29.4 meters per second and the angle of elevation is 30 degrees. Now our first task is to calculate the x and the y component of this initial velocity. So that's a very straightforward trig question. So using u for initial velocities and subscript x, I have seen people say v0, comma x to mean the same thing, where v0 is initial velocity. I find that a little bit more cumbersome to write that, but be aware of it. So horizontal is a cosine ratio of our angle, 29.4 cosine 30 degrees, and I find that to be 25.5 meters per second. The initial vertical velocity, sine of the 30 degrees, and I make that as 14.7 meters per second. I'll be working through figure accuracy throughout this question, which again is a fairly typical choice. Now, the first part of the question asks us to write a vector equation as well as a Cartesian equation for the motion of these things. So let's do the vector equation first. So we're going to make the assumption that the horizontal acceleration is 0, no air resistance there, and that the vertical acceleration equals negative 9.8. So solely the influence of gravity. I should have put a little subscripted y in there to show vertical. So we have to treat the two separately. Now, it's a constant acceleration situation. We can rely on our typical equations of motion. So let's begin with writing the x coordinate. Now normally we would say something like ut plus 1/2 at squared. Of course, acceleration is 0 in the horizontal sense, and this would be ux, the horizontal component of the velocity. Now we made that to be 25.5 by t. Let's just call that equation 1. I'm sure we'll need to come back to that. The vertical displacement, u times t plus 1/2 at squared. Now it'll be the y component of the starting velocity and the y component of acceleration. That was 14.7 times t. Gravity being negative 9.8, this becomes minus 4.9 t squared. Let's call that equation 2. I'm absolutely sure we will need to refer back to these. And our work is almost done. The vector equation, so the position vector r as a function of time, it'll be the x coordinate, 25.5 t, multiplied by basis vector I, plus the y coordinate, 14.7 t minus 4.9 t squared, by basis vector j. That's our first answer. That's the vector equation for the particle, the path that it follows. We also had to do the Cartesian equation. So we've done these in the past, so I'll go fairly quickly. From equation number 1 above, we could see that t equals x over 25.5. Then we will sub that into equation 2. We will have 14.7 by x over 25.5 minus 4.9. Sorry, got my decimal point in the wrong place then, didn't I? 25.5, and that one is squared. Now when I worked that out, I got decimal 577x minus 0.00756x squared. I think maybe we should have called that one equation 3, the vector equation, and let's call this one equation 4. It probably should have some highlight there as well. That's the Cartesian equation. Now hopefully you recognise this as the equation of a parabola, and the fact that the value of a is negative, we should be having a sad face parabola, and that all makes perfect sense when you consider that our projectile would go like this and then come back down and hit the ground somewhere over there. Our first coordinate would be 0, 0. Our next coordinate over here, well, we don't know that, but we could work it out. And that, I think, is the object of the next part of the question. Sorry, I was trying to rub that out then. So we've done the vector and the Cartesian equation. Part B of the question, find the time of flight. Well, time of flight we can use any of equation 1, 2, 3 or 4. Equation 4 is not going to be a good choice because time doesn't appear in that equation. Equation 3, time does appear in the equation, but the trouble is we have too many things we don't know. We don't know how far the thing has moved forwards in the time that it has come back down to ground. I think we'd be better off to go with one of our little components here, and equation 2 is the one. If we're looking for time of flight, then we could use equation 2 to solve for t if we knew the y value. Now let's stop for a moment and think about that. There's my projectile, starts at 0, 0, and it does this. I don't know the x value of this point, but I do know the y value of that point. The y value must be 0. So I'm going to use equation 2. Equation 2 said that y equaled 14.7t. Sorry, there was a bit of a knock at the door then, don't know what that was about. Minus 4.9 t squared. If I substitute 0, and, oh, sorry, losing my train of thought there. And I might also factor out one of these t's. So the 0 for y came from that fact that it lands when it's assuming that the ground was horizontal, I suppose. Now, what do we do then? Well, null factor law. T could equal 0, or in the case that 14.7 minus 4.9 t equals 0, t would come out to be 14.7 over 4.9, and that is 3 seconds. Let's interpret both of those. T equals 0 would represent this point here, the starting point. I'm not really interested in that as a solution. It's true, but it's not very interesting. T equals 3 would be this point over here. That's definitely the one I want to know. The time of flight is how long it takes to fly through the air and then come back down to ground level. And again, I'm making the assumption here that the ground was horizontal. So 3 seconds for time of flight. Next question was to find the range of the projectile. The range means how far, or pretty much what this x-coordinate is here, how far it has moved. Now, we've got a time of 3. We could probably not. We could use this one because we know y equals 0, and we could solve for x. It'd be a bit harder than we need to make it. Number 1 would be the easiest. We have the time equals 3. We could substitute directly. So range, we will use equation 1. X equals 25.5 by t and that is 76.5 meters. Very nice. Final question. Find the maximum height. And these are all the typical things that projectile questions want you to answer. Time of flight, range, maximum height. Now there's 4 equations that we've got to work with here that we could use. I could, let's see, maximum height on my diagram is going to be at this point. Now it is symmetrical motion. I could claim by symmetry that the time to reach this point is 1.5 seconds. That's true as long as the ground is level. Now, in this case it is, so it's a good simple solution. Once we have the time of 1.5 and we want to know the height, we could go back to equation 2 here, substitute 1.5 into this, and we'll get the answer. So, by symmetry, time would be 1.5, and now from equation 2, y equaled 14.7t minus 4.9t squared and I calculate that to give 11.0 meters. That's enough for now. The video's got a little bit too long. I will have a second part to this where I'm talking about technology-based solutions to this question. Okay, thanks for now. Thanks for that, and I'll see you next time.